In the previous videos, we talked about activating and deactivating groups. So basically, how does a group that's already on the benzene ring affect how well that reaction is going to take place? So whether that ring is going to be more reactive or less reactive in a subsequent electrophilic aromatic substitution reaction. Now we're going to talk about how does that group that's already attached to the ring affect where that new group is going to end up on the ring. So this is going to be very important for product structures that we're going to be drawing and what's going to be our major products. And so the first thing we're going to talk about is groups that are going to direct the new incoming group to go either ortho or para to it. And so let's take a look at this example down here. We have an OCH3 group attached to the ring, and we're trying to do a nitration reaction. So HNO3, H2SO4, that's going to give us a nitro group on the ring through the mechanism that we saw in previous videos. And so we have three possibilities for the products. Because this benzene ring is flat, really the only things that can change is that location on the ring for where that nitro group is going to end up. So we have either the position right next to the group that's already on the ring, so that we call the ortho position when they're on carbons right next to each other. This side over here on the left would also be an ortho position, but it would be the same product as the one that we've drawn here because it's still just one carbon apart and this ring is flat. We could just flip it over and we would have this structure here. So ortho. We have meta as another product, so we could put this group one carbon away. So it could go on this carbon here. Alternatively, we could have shown it on this carbon over here because it's also one carbon away and that ring is flat. So again, we could flip it over and then we would have this same product. So these two, we could have drawn them two different ways, but these are the only two, ortho and meta. And then we have para as our last option, and that's where we're putting this new group directly across the ring. This is the only way we can draw the para product because there's only one position directly across the ring from the group that's already on the ring. And so what we're going to take a look at is for these three products, how can we tell which one or which ones are going to be favored? And what this really comes down to is how this group that's already attached on the ring is affecting that rhenium ion intermediate. So we saw that in one of our first mechanism videos to show that, even though we break aromaticity in this reaction, we do have a relatively resonance stabilized intermediate. And so what we're going to look at is those resonance structures of that rhenium ion to see which pathways are going to be lower in energy. And to ask ourselves which pathways are going to be lower in energy, we're going to see how this group ends up affecting that rhenium ion. So this is a lot of resonance structure drawing out, and I highly suggest that you do draw out all of these resonance structures, making sure that when you're copying this down, you're paying attention to where that positive is and where you're moving your electrons in your double bond, because it can, if you're not paying attention, you can kind of mess it up pretty easily. So just make sure you're paying attention when you're writing these down. What we're going to start with is taking a look at the ortho pathway. So with this one, just based on the way that I've drawn the double bonds, I use the bond up at the top there to go and attack. I skipped right to that super electrophile step because we're not focusing on the mechanism here. We're focusing on the products that are produced. And so in our ortho pathway, if we do that attack, we will always have in our resonance structure that nitro group at that same position because it's all still ortho. We're just drawing the resonance structure. So we'd originally get a positive charge there. We could move the pi bonds around the ring to help stabilize that. But in addition, because of the group that we have, we see that it actually in this structure, it ends up next to the positive charge. And we have to think about how is this group going to affect that positive charge. We do have lone pairs on this specific group. And what we can do with those lone pairs is we can actually produce another resonance structure because we could bring those down and that would give us an additional resonance structure in this pathway. So that's going to bring that positive onto that oxygen. This is actually a very important resonance structure as well because this resonance structure, all the atoms have octets. And so this is actually what that molecule, that intermediate is going to look like mostly because this is going to contribute most to the resonance hybrid for this intermediate. So this is a really important structure and we're able to get to this structure because of that group that is on the ring. It ends up right next to the positive charge and we can donate the electron density to it through resonance like that. For the meta pathway, we see that what's different about this pathway first, I used a bond at the bottom just because that's where I drew that bond. We do need to get it onto this position, and so we do need to use a double bond that includes that position, so we can't use that top one anymore. So I use that one at the bottom. Then the nitro group goes into that meta position. It's there on every single structure, and we're doing resonance, and we see that the positive charge ends up in different locations in the meta pathway versus the ortho pathway. So we don't ever actually get this positive charge next to the group that's already on the ring. And so this group that's on the ring can't really affect that positive charge very much in that meta pathway. It sometimes is going to be a good thing. Sometimes it's going to not be a good thing. And in this case, because we can't draw an extra resonance structure, you might already be thinking, well, this is probably not a good thing for this particular group because we don't get that extra stabilization that we had in the ortho pathway. So now looking at that para pathway, using that same double bonds, we do need to put the nitro group on the bottom for the para pathway. We get that positive charge, we do our resonance, we see that again, that positive charge ends up next to our group. And so we can again do resonance, bring that down, and draw that extra resonance structure where all the atoms have octets, and we're able to stabilize that charge further. And then we also have the last resonance structure, just bringing that bond up here as well. So what we see and what we can get from these three pathways is that in both the ortho and the para pathway, we have an extra stabilization of this positive charge. And in this case, it comes because the oxygen is able to use its lone pairs and actually make another resonance structure. And so we're actually making this intermediate more stable in the para and ortho pathways. This does not happen in the meta pathways. So what this is going to mean is that our ortho and para pathways are actually going to be lower in energy because their intermediate is going to be lower in energy because it's going to be more stabilized. And in this case, it's more stabilized because it has an extra resonance structure. So ortho and para pathways are favored. That's because that positive charge ends up next to a group that's capable of stabilizing it through resonance. What we have to note is that we're not always going to be able to make an extra resonance structure in those ortho and para pathways for our ortho and para directors. What can happen is that we could have an alkyl group, for example, attached. And for this one, it's actually going to stabilize when the positive charge ends up next to it. It's not going to be able to make another resonance structure with it, but it will still make this resonance structure more stable because we are going to be able to donate through hyperconjugation. And so the ortho and para pathways, even for our weak activating groups, they're also going to be more stable, even though they're only going to have three structures, just like the other pathways. What's going to happen is we're going to have increased stability because of hyperconjugation. And so don't forget about that. We're not always going to be able to draw another resonance structure in the ortho and para pathways. We have to think about hyperconjugation as well for stabilizing this positive charge. So we're going to see that the weak activating groups also are ortho-para. So basically what we can say, because we know that the strong and moderate activating groups donate electron density through resonance to that benzene ring when it was kind of nice and neutral. In the previous videos, we saw that those lone pairs being next to that ring, if we're able to donate resonance into that neutral ring, we're also able to donate it to that positive charge. And so they'll be able to extra stabilize those ortho and para pathways. So strong and moderate activating groups are going to be ortho para directors. Weak activating groups are also going to be ortho para directors because we'll be able to stabilize through hyperconjugation when that positive ends up next to the group. And so what we can say, all activating groups are ortho and para directors. We also have an exception that we might not expect at first, and that is because our weak deactivating groups, so those were mostly our halogens, these are also orthopara directors because when the positive ends up next to them, although we saw that in the neutral ring, this group is pulling away because it's electronegative, and so it pulls electron density out of the ring very weakly, a weak type of induction, but it still pulls it out of the ring while it's nice and neutral. When there's a positive charge beside it, that bromine kind of steps up and uses its lone pairs to help stabilize. So we actually do see a little bit of resonance with the halogen atoms and that positive charge. And this is kind of the situation is a little bit of an emergency kind of for this molecule. It really needs to help get more stabilized because it just broke its aromaticity. And so that kind of causes that bromine to step up and actually overlap a little bit with that positive charge, overlap its orbital a little bit with that positive, and actually produce a resonance structure like the one shown. And so we see that with halogens, they're also ortho para directors because they can also stabilize that ortho and para pathway. And remember that the ortho and para pathway is the one that puts that positive right next to the group that's already on the ring. And that's going to be the case for any group we have on the ring. Ortho and para will put that positive charge right next to that group, and meta will always avoid putting it next to the group. And we're going to see in the next video how that could actually be a good thing depending on what that group is attached to the ring. Sometimes we don't want that positive to be beside that group because it could make it worse. In this case, these groups were in this video were all making that positive charge better. They were donating electronicity to it, and so they're all ortho para directors.